Hello everybody, this is Mr. Pope from WGSB, and this is going to be the first in the Wednesday sessions I do with you on calculus, and the first thing we're going to be looking at is differentiation. So before I plod on with some basic mechanical concepts of differentiation, there's a bit of a bad rap with calculus, especially in television shows. It always seems to be the case that American high school dramas or horrors or just general romance movies in a high school setting or just any school setting, although it's not really talked about that much in England, but it seems to be someone's always failing calc class, or calculus is really kicking their butts or whatever, and it seems to be something that people struggle with in their teens. And I'd like to just kind of put that to rest, really. So what is calculus? Calculus, the clue is in the name. It's to do with calculating things, but essentially it's dealing with calculations where objects either go infinitesimally small or infinitely big. Okay, whenever you've got a calculation where things go infinitesimally small or infinitely big, you're probably going to be using calculus to solve it. So here's hopefully a simple example that, well, maybe you can convince yourselves is true. Let's say I've got a fence, and that fence is 12 meters long. Okay, and let's suppose this fence is bendy, so I can bend it into any shape I want to, any amounts I can. It's metal of some kind, or like some malleable fabric. It doesn't particularly matter, and I can arrange it in any shape I want. But let's suppose, me being weird, I want to arrange it with posts. So what will happen is there'll be a post, and then there'll be a sheet of fence, and then a post and a sheet of fence, and stuff like that. Okay, now let's suppose I am interested in seeing what kind of shapes I will get with that post. So let's suppose the first obvious case is, suppose I arrange an area such that all four sides are 4 meters, and it encloses an equilateral triangle, just for argument's sake. So that could be one configuration. Let's suppose I get more daring and I make a square, and this time each of the sides are 3 meters. Okay, and then let's suppose I go one step further and I use 5 posts this time. I've still only got 12 meters of fence, and I create a regular polygon, a regular pentagon in this case. So each of these are 12 over 5 meters long. Okay, and I could continue this pattern for over and over and over. So the question is, if I have only got a finite amount of fence, which is 12 meters, let's have a look about it. Let's note some key points down. Well, first of all, let's count the number of posts at each time, and let's count the edge length of each edge if they're all the same. So maybe I shouldn't have made that red. Okay, so how many posts are in the first one? There's 3 posts. 1, 2, 3. How many posts in the second one? 1, 2, 3, 4. There's 4. How many posts in the next one? 2, 3, 4, 5. There's 5, and so on. Edges. Well, let's think about it. The edge length in the first one is 4 meters, and then it's 3 meters, and then it's 12 over 5 meters, and so on and so on. The question is, I am interested in what kind of shape will I draw if I have an infinite amount of posts and the edges become almost but not quite zero, infinitely close to zero. Okay, can you see what kind of shape this fence is going to be like or behave like? And if you guessed that it would approximate a circle and there'd be an infinite amount of posts with infinitely tiny fence between each of the posts, then you're on the right track. Okay, we could have taken the idea from the posts and that what happens in the limit, and we're going to be talking about limits at some point, but not today, what happens in the limit as the posts tend to infinity. Now you can probably say, well, infinity is infinity, you can't ever get there. And that's true, but we just pretend like what's the overall behavior? I mean, let's pretend, what is this behaving like? And we say in the limit, as the posts tend to infinity, this fence appears to be a circular shape. Or we could have spun it the other way and said, well, what happens to the shape when all of the edges, equal length edges, tend in the limit to zero? Well, that's going to be the same answer. So it doesn't matter if we're dealing with something infinitely big in the cases of the fence, or we're dealing with something infinitely small with the lengths of the edges in this case. Now, we could have addressed this problem from a calculus point of view, and after today's session, I challenge you to go away and formulate this in another way that makes sense in terms of calculus, and hopefully you should be able to do that. So essentially, calculus is looking at long-term behavior, whether things get really, really big or really, really small. So one part of it is this concept called differentiation. Okay, and if we're going to play a little opposite game, then we're going to have operators on this side, and we're going to have operators on the other side, but let's call them inverse operators. Okay, so let's play an easy game. If I say, and I add two things, well, if I wanted to add by 5, the opposite to that would be subtracting by 5. So the opposite operator for adding is subtracting. Fair enough. Well, what's the opposite operator, the inverse operator for multiplying? Well, that's fairly easy. That's dividing. Okay. Well, what's the opposite operator if I've got something to the power n? I take the nth power of something. Well, up to GCSE, you should be fairly familiar. That's when you take the nth root of something. Okay. Let's say you've got n to the power of something. How do you get that something? Well, if you've seen the number theory video that I've done on Monday, then that will be log base n of that something. Oh, sorry, that would be log base n of n to the something will get the something. Undoing powers using logarithms. And finally, operators we're looking at today is d by d, and let's call this variable x for now, and you'll see why in a second. And again, there is an inverse operator for differentiation. We'll cover that soon. In actual fact, if you look at the schedule, you can probably tell which day it's coming up. You're more than welcome to look ahead. But this thing here is a differential operator. Okay, and you're probably thinking, like, what on earth is that? What is this d by dx stuff? Okay, first of all, what's rather confusing is this is not a fraction. It's an operator. But There are special circumstances where this can be treated like a fraction, and it's only for the sake of analogy. Okay, you do not treat it like a fraction, like 1/4 or 2/3. That's not how it works. However, later on in the course, when we look at the chain rule and various other ways of differentiating things, then you can treat it like a fraction. Okay. So at this point, calculus, usually if I wanted to say solve something using calculus, then I'm talking about these two operators here, i.e. differentiation and the opposite of differentiation, which I'll call anti-derivatives. Differentiation, derivatives, the same thing. Okay, so at the moment, calculus, you should have an idea in your mind that it's to do with the behavior of functions and systems when things or objects become infinitely large or infinitesimally small. And the d by dx operator, or d by d anything, I mean it could be d by d theta, it could be d by dt, and so on and so on. The point is, this object here is the variable we're dealing with. And the way to look at it is, let's suppose I have a function of x. Then if I apply the operator d by dx to it, just in the same way as I could do the 2 times f of x operator to it. So what's that saying? The multiplying is just an operator, that's just timesing the function by 2, and d by dx is just an operator to that function. It's going to do something to it. It might change it. It might not, but it probably will. Okay, what does this statement mean? It means I am going to see, I'm looking at the change in f of x, and then on the bottom of this fraction, with respect to, and you'll see in a lot of textbooks this WRT, which stands for with respect to x, the bottom variable. So what this statement is saying is, when I use d by dx on f of x, I'm trying to calculate how does the function f of x change as you increase x. Okay, so let's look at some examples. Or rather, let's look at a function y equals, I don't know, let's say 2x plus 3. Okay, well, let's suppose I have no idea how to differentiate things. So I'm just going to plot y equals 2x plus 3. So here it is, like that. And 2x plus 3 means it's going to cross the y-axis at 3, and it's going to have a gradient of 2. Okay, because this is a function of x in the form y equals mx plus c. Okay, where m is the gradient and c is the y-intercept. Okay, so the question is, if I apply the d by dx operator to y, that means I have to apply the d by dx operator to 2x plus 3. And now let's think about it. d by dx of y, I'm applying d by dx of y. Well, we write that as dy by dx, like so. Now what does that tell me? Where have you seen the change in y over the change in x? Well, the gradient of a line is the change in y over the change in x. Now you might have seen these little triangles before. It's the Greek letter delta, which just means a measurable change. And there's no coincidence that we use the Greek letter delta for a measurable change and dy by dx for an infinitesimally small, you can't measure it change. It's in the limit as something is tending to infinitesimally small or infinitely big. So this is relatively straightforward. What is the gradient of this function everywhere? Well, it's always 2. So with no calculation, I can tell in this example that it's 2. So immediately, in the context of dy by dx, I get that dy by dx is the gradient function. Okay, fine. That's pretty cool. But here's the problem. This is a straight line. How could I do this? How could I extend this so that I can differentiate any function of x like I'm trying to claim over here? Because d by dx of f of x will spit out d of f of x over dx. And instead of writing that mouthful, we just write f dashed of x, where f dashed is the first derivative. And we can keep repeating this process. For example, f double dashed of x is when I've differentiated f dashed of x, and that's the same as if I've differentiated normal f of x twice. I differentiate it once, and then whatever that result is, I differentiate it again. The dashes are just a quick notational thing of just keeping a track of how many times you differentiated it. Okay, let's suppose, what we're going to be looking at now is what's called differentiation by first principles. Okay, now this is going to be hopefully not too difficult to understand, but I totally get it if it blows your mind. It's honestly not that bad. So, follow me. Let's suppose I've got a function y equals f of x. And by the way, let's remind ourselves, x is some input. There's my x values, there's my y values. X is just an input. F is just a function. That means I put the input x into that function and it spits out y, which is the outputs. Okay, some of you have seen this in primary school with your function machines. For example, you've got an input, you've got a really basic function like timesing by 2, and then you've got the output. In this case, if the input was x and the output was y and the function f of x was just 2x, then essentially you've got an input of x, the f of x function turns the x into 2x, and that becomes y. So in this example, we've got y equals 2x. Hopefully this shouldn't be too hard to understand. But we're trying to go away from this linear thing. So any function you like, I don't know, we like that. Who cares? Well, let's make it even weirder. We like that. Okay. So that's my y equals f of x function. Okay. So let's suppose I've got a point here, and that point, if I trace it down to the x-axis, this gives me a value of x. Okay, and if I trace it over, the y value is just f of x, like so. Okay, and let's suppose I want to work out the gradient of that function anywhere. So no matter where the x is, I can just go boom, that's the gradient, that's the steepness of the curve at that point. By the way, this red line we'll talk about in a second, but at that point, that is like a measure of steepness. Because we're on that part of the hill, if you were standing on it, the hill would be fairly shallow, pointing upwards to the right. If I was over here on the hill, then clearly the steepness of the hill is pointing downwards. It's fairly steep, and we'll call that a negative gradient. Hopefully that's not too difficult to see. So let's go back. How did we work out the gradient? Well, the gradient we know is dy by dx, that's the whole point of it, but it was also some measurable change in y over some measurable change in x. Okay, well, that's going to be an approximation as well, and you'll see why. Okay, let's suppose I pick another value of x over here, and let's say that the distance between these two x's is h. Then this value of x is x plus h. Okay, traditionally we use the letter h, and you'll see this in textbooks and various other things. So, what would the y value be of x plus h? Well, that's easy. I trace it over, and this will be the function when I put x plus h in as the input. And then what is the change in y over change in x? Well, the change in y, think about it, here's the gradient between the 2 points, from there to there. The change in y is going to be the change in height, or in this case it's f of x minus f of x plus h, divided by the change in x. Well, that's going to be x minus x plus h, isn't it? Because if I start here, that corresponds to the x, so I've got to minus the x plus h. It's this distance. And that will give me the blue line. And then when we tidy all this up, well, x minus x plus h is going to be minus h. And I've got f of x minus f of x plus h. I don't like that there's a minus on the bottom, so if I times by minus 1 top and bottom of this fraction, I get f of x plus h minus f of x over h. And this, I'm claiming, is a good approximator for the gradient. Well, let's have a look at it. How good is that blue line approximating the gradient of the red line? Well, it's pretty naff, isn't it? The red line's pointing slightly upwards and the blue line is pointing massively downwards. Okay, what could I do to the blue line, bearing in mind that x and fx are fixed, because that's the point in which I want to know the gradient? How could I amend this? Well, let's suppose I make h smaller. Let's call this was h1, and this is h1 there. Well, let's say I now make h smaller, so now h is here. Well, that's going to go, that point is going to be x. Let's say this is h2, this becomes xh2. Well, no. Let's say h I've made smaller, so x plus h is there. If I trace it up, the x value is here. And if I trace it along, this point here is now f of x plus h. This is h plus 1. And now, if I use purple, the gradient would be between the 2 points, would be the gradient of that purple line. Ooh, it's not as steep negative anymore, is it? What do you think I would need to do to get that from the blue section to the purple section to the red section? Would I have to make h bigger or smaller? Well, look, I would have to make h as small as possible, wouldn't I? The smaller the h is, the nearer these 2 points are, and the more accurate the tangent is, the gradient of that point. But here's the problem. when h is 0, it is exactly the gradient, and that's what we want. But the problem is we've got a thing here, we've got an expression for the gradient, but we're dividing by h, and we can't divide by 0. That's just not really a dumb thing, and we'll explain that a little bit later when we're sketching graphs. But dividing by 0 is not a good thing to do. So what have I said before? Well, we're going to use calculus. We're going to pretend when it gets infinitesimally small. So the get around for this is we say the gradient is exactly this thing. Let me move over a little bit. In the limit, and I'll just put lim, L-I-M, when h arrow tends to 0. So the gradient function, which by the way is f dashed of x, which is another way of saying dy by dx, when y is a function of x, is the limit of f of x plus h minus f of x all over h. Now you're probably thinking, okay, well, how does that relate to our previous example when f of x was 2x plus 3? Okay, let's give it a whirl. So, what was it? Our function of x was 2x plus 3. So what would f of x plus h be? Well, that would be 2 lots of x plus h plus 3. Can you notice how that when x is the input, x plus h is the input, so I just replace all the x's with x plus h. If you want to, you can put a bracket around the variable just to remind yourself that's what needs to happen. And this isn't too bad, because 2 lots of x plus h is 2x plus 2h plus 3. Okay, now let's do what this says. We're going to do f of x plus h, so the limit as h tends to 0, this is f dash of x, of the fraction over h, f of x plus h, which we worked out to be 2x plus 2h plus 3, minus f of x, which is going to be minus brackets 2x plus 3. Okay. Can you see how the 2x and that 2x will cancel? Because I've got a minus 2x here, and I've got a minus 3 popping out, so that 3 and that 3 will cancel. Can you see how I've slashed in particular orientations? So that 3 and that 3 cancel because I've slashed from top left to bottom right, and that 2x and that 2x have cancelled because I've slashed from top right to bottom left. So what happens here is I've got the limit of h tends to 0 of the only term left on the top is 2h, and that's over h. So this is going to be a limit as h tends to 0 of, well, 2h over h cancels, I'm left with 2. Now this is really easy because there's no h here. It's completely what we call independent of h. So the answer there is, the answer's 2. That's beautiful because that completely agrees with our answer beforehand. So it's consistent. And by the way, this will work with any function. Let's try something a little more crazy. Let's suppose I've got something a bit more exotic. Let's say I've got y equals x squared. So what does that look like on a graph? Something like that. It's a U-shaped parabola. Well, this is more interesting because depending where you are, let's say the x value there, the gradient will be positive. And let's say I go back here to a negative x, then the gradient is negative. Or let's say I'm interested when x is 0, the gradient is 0 there. So the gradient, so dy by dx is 0 here. Dy by dx is positive here. And dy by dx is negative there. There's no way to calculate absolute values, or it's different everywhere. Okay, for all different values of x, it's going to be different, so this isn't cool. So let's use our formula. So dy by dx is the limit as h tends to 0 of all over h, the function squared, no, just the function, which is f of x squared, but you replace x with x plus h, and then minus the function itself, which is x squared. Notice how if f of x is x squared, then f of x plus h is just x plus h all squared. Okay, so that means the limit of h tends to. Now be very careful here. Whoops, that was terrible. Because on the bottom is h, on the top is x squared, but x plus h all squared, that is technically saying x plus h times by x plus h. You have the quantity x plus h times by itself twice. So, I mean, when you're good at this, you can just tell it's x squared plus 2xh plus h squared, but I'm just doing it step by step so nobody gets lost. Okay, x times x is x squared. I'm going to have a h times x plus another h times x there, which is 2 lots of hx, plus a h times h, which is h squared, and then minus an x squared. Okay, right. So this is the limit as h tends to 0 of, now let's look at this. This is all over h. The x squareds cancel, and I'm just left with 2hx plus h squared on the top. Interesting. So that's the limit as h tends to 0. Can we factorize the top? Can we tidy it up? Well, both of the top terms have a factor of h involved. So this is going to be h lots of 2x plus h. That's great because there's a h top and bottom we can cancel, so that's 2x plus h over 1. So it's the limit as h tends to 0 of 2x plus h. Now what we do in the business is when h tends to 0, we just put the h with a line through it and put a 0 to indicate that it evaluates to 0. So what does this become? It becomes 2x plus 0, which is 2x. That's fantastic. So the upshot of this is that dy by dx for y equals x squared is 2x. That's incredibly powerful. So if I said the x value of here was 2, then when I trace it up there, then the gradient dy by dx is actually 2 times the x value, which is 4, which means at that point it's as steep as a triangle with base 1 and height 4. It's that steep. Well, this also satisfies 2 lots of 0 is 0, so that works. And then let's suppose I've got minus 1 back here. Well, then dy by dx would be 2 lots of minus 1, which is minus 2, which has got the same steepness as if you went 1 along, but this time 2 down. So it's that steep. Okay. Now, you're probably thinking, oh God, this was such a long process. What the hell? I don't want to have to keep doing this over and over and over again. And luckily for you, this is exactly what we're talking about when we're talking about the power rule for polynomials. Now, you can differentiate pretty much every function that I'm going to show you. For polynomials, though, they're pretty easy to differentiate. There's a few caveats there, but in general, there's a power rule, so you don't have to worry about that kind of thing. So let's say y. Okay, let's have the power rule. This is important. If y equals kx to the n, okay, and n can be, well, n can be any rational number, a quotient. There are a few exceptions to that. and we'll talk about them. But the rule is, if you want to differentiate a function of x, you bring the n down as a factor. So this is n times k times x, and then you subtract 1 from the power. Okay, now here's a couple of like exceptions, or rather special cases. Okay, if I've got x to the 0, which is essentially 1, or I've got 3 times that, which is essentially 1 times 3, then this differentiates to 0. It does not, I repeat, differentiate to 0 times 3 times x to the minus 1, which is 0 anyway, but I mean, well, it's debatable at that point. Essentially, what I'm trying to say is that if you differentiate respect to any variable, a constant, it will go to 0. Okay? So, let's try some examples. Let's say y equals 3x squared. Well, that's going to be dy by dx. If I differentiate both sides, I bring the 2 down. So I've got a 2 times the 3, which is 6. And then I've got x to the power of 2 minus 1, which is 1, which is just 6x. Okay, so let's have a look. If y equals x squared gave me dy by dx is 2x, then did timesing by 3 give me 3 lots of 2x? Yes, it did. Now, this isn't necessarily a proof in itself, but a consequence. And you can prove this to yourself. And essentially, if you've got this thing, the derivatives by first principles, you can probably prove it to yourself. But let's do a couple more examples. There's 2 main things. One, if I differentiate dy by dx and I have, let's say, some k times a function of x, where k is a constant, then that is the same as k times, whoops, daisy, this is gibberish. That is the same as k times, if I was to just differentiate the function itself. Okay, so what does this mean? It means I can pull constant factors out of the derivative. Okay, so if there was a k in there before, so what we just essentially done previously is if I wanted to differentiate 3x squared, that is the same as 3 lots of the differentiation of x squared, which is the same as 3 lots of 2x, which is 6x. Okay, so first key point, you can take constant factors out. Next key point is if I was to differentiate f of x, but plus, let's say, a different function of x, that is the same as if I differentiated them individually and then added them together. Okay, so this is another key point. What this essentially allows us to do is differentiate term by term, and it still preserves the answer. And if you want to, I mean, we can prove this fairly quickly. If I want to differentiate this thing, this is the limit as h tends to 0 of f of x plus h plus g of x plus h, that's a quantity, minus f of x plus g of x, and this is all over h. And then you can isolate bits out, because this is going to the limit as h tends to 0 of f of x plus h minus f of x all over h plus g of x plus h minus g of x over h. And then you can probably see the next step after that is we just take the limit of this thing and put it here, plus the limit as h tends to 0 of of this thing and put it here, and it all works out. Essentially, we've separated up the calculation to do with the limit, and so differentiating multiple functions, you know, is pretty easy. Now, these aren't the only two things, but these properties are because differentiation is what's called a linear operator. Okay, and the inverse operation of differentiation does the same thing. Okay, so you can take out constants, you can add up. When you're adding up functions and differentiating them, that's the same as differentiating them individually, then adding them up. Differentiation is a linear operator. If you want to Google more about that, that's absolutely fine. But I feel like 40 minutes in, I need to start doing some examples. But at the moment, that is very, very basic calculus by first principles. And in general, first year, year 12 stuff, we really use the power rule when we're differentiating things. Now, I'm going to go through some examples because in some cases you actually have to algebraically manipulate what's going on first. So let's tidy this up. Okay, so let's look at some examples. So, given that y equals 8x cubed minus 4 root x plus 3x squared plus 2 over x, where x is positive, find dy by dx. Okay, first thing I'm going to do is I'm going to tidy this up and I'm going to write it what's called index form. Okay, so if you want to pause it and have a go yourself, that's absolutely fine. But 8x cubed is 8x cubed. Minus 4 root x is the same as 4x to the half. And now, this term is essentially saying 3x squared divided by x, which is 3x, plus 2 divided by x, and 2 over x is the same as 2x to the minus 1. And now we are ready to compute the derivative or differentiate this function with respect to x. Those phrases mean the same thing. So, all of these terms have unique powers of x. If there isn't a number there, that just means it's to the 1. Okay, so 8x cubed, what will that differentiate to? Well, the 3 comes down, so the 3 times 8 is 24, and then it's x to 1 lower power than 3, which is 2. Easy peasy. Next, the half comes down, so minus 4 times a half is minus 2, then x, and then a half minus 1 is minus a half. Next one, the 1 comes down, so 1 times 3 is 3, and then it becomes x to the 0, and x to the 0 is just a constant term, so that just stays as plus 3. Next up, minus 1 comes down, 2 times minus 1 is minus 2, and then this is x to the power of, and then minus 1 minus another 1 is minus 2, so that indeed becomes 2x to the minus 2. So that was a fairly easy question, and that would be my final answer. 24x squared minus 2x to the minus half plus 3 minus 2x to the minus 2. That is dy by dx in that example. Okay, next one. If you want to give it a go yourself, pause the video. Okay, this is a fairly easy one. 4 comes down, so 4 times 1 is 4, and this is x to the subtract 1 from that power, so that's 3. Third comes down, so that's plus a third, x, and when I take third minus 1, that's going to be minus 2/3. And then 3 is essentially 3x to the 0. And we know what happens there. The 0 comes down, 0 times 3 is 0. So that's plus a 0, so it's just going to give those two terms. Another way of thinking about it is constant terms differentiate to 0. And why is that? Well, because if I have a function y equals k, where k is a constant, this is just going to be a horizontal line where it cuts the y-axis at k, and clearly that gradient is 0 because it's flat everywhere. dy by dx equals 0 in that case. So it's contributing nothing. Okay, the curve C has this equation. Find dy dx in its simplest form. If you want to have a go, pause the video and go for it. Okay, so no magic here. What you have to do is expand the top bit and then divide everything by x. So x times x will be x squared. 3x minus 8x is minus 5x, and 3 times minus 8 is minus 24. And this is all going to be over x. So y is, divide each term by x. X squared over x is x, minus 5x over x is minus 5, and minus 24 over x is minus 24x to the minus 1. Really easy peasy now. To find dy by dx, we'll apply the power rule. So this is x to the 1. So I bring the 1 down, so that's 1. Then x to the, and then 1 minus 1 is 0. X to the 0 is a constant, so that's fine. Minus 5, when I differentiate it, that's a constant, so that disappears. And then next, minus 1 comes down, so minus 1 times minus 24 is plus 24. And then I subtract 1 from the power, so this is x to the minus 2. Easy peasy lemon squeezy. Dy by dx is 1 plus 24x to the minus 2. Okay. Next up, if y equals 2x cubed plus 3 over x squared, where x cannot equal 0, this is clearly the case because you'd be dividing by 0 here if it was, then find dy by dx. Okay, again, I'm going to get this in index form, so y equals 2x cubed plus 3x to the minus 2, because if I'm dividing by x squared, that's the same as timesing by x to the minus 2. Differentiating this is really easy. The 3 comes down, so that's 6. X subtract a power, so that's 2. And then the minus 2 comes down, so it's minus 6. X subtract a power, that's minus 3. So there's your answer for that one. Easy peasy, lemon squeezy. It's just mechanical stuff, asking you to find dy dx. It's not in context. I've gone over way too much context for it, but it's pretty easy. Now what we're going to be looking at is some geometrical interpretations, and that's mainly tangents and normals. So I'm not going to go through too many examples. In actual fact, I probably won't do any because I've got some examples down there. Okay, so let's give it a whirl. Now, remember I was talking about this. I had my function f of x looking something like that maybe. And I'm saying if that is the point x, or let's call that a, b, where f of a equals b. That's saying if I plug a into my function, it spits out b. Then f dashed of a is the gradient of the curve f of x at x equals a. But it's also the gradient of this thing. But it's also the gradient of the tangent to the curve. And now the way conceptually that I can explain a tangent is, imagine a tangent line is just a ruler, and that ruler has this gradient, and it comes down, and it stops when it just touches the surface. So it only touches the curve at one point, like a seesaw. And that gradient of that tangent is going to match the surface that it's on. Okay, so let's suppose the function was, I don't know, let's say it was x cubed plus 2x squared plus x. I don't know, who knows. then if I wanted to evaluate the derivative, f dashed of x to find the gradient, that would be 3x squared plus 4x plus 1. And suppose, I don't know, I wanted to work out the tangent at the point when x equals 1. Well, I'd find out what the gradient of the curve is when x equals 1. So that's 3 lots of 1 squared plus 4 lots of 1 plus 1. So that's 3 plus 4 plus 1, so that curve is 8. So because a tangent is a straight line, that's going to be y equals mx plus c, and know the curve has the form y equals 8x plus something. And now, what does that tangent and the curve have in common? Well, they both have that point x equals 1 and y equals what? And to work out what the y value is, you can just plug the x value back into the original function. Well, that's going to be 1 cubed plus 2 lots of 1 squared, so that's 3 so far, plus 1, that's 4. So now I know that when y is 4, that's going to be 8 lots of 1 plus c. So 4 equals 8 plus c, so c equals negative 4. So that means the equation of the tangent is y equals 8x minus 4. Now that's clearly contrary to the diagram that I've drawn, because I just made this thing up, this f of x function up. But if I were to draw the f of x graph, which looks like x cubed plus 2x squared plus x, and I knew that the point x equals 1 and y equals 4 is on it, and that I wanted to work out the tangent, then the equation of that tangent line that just touches the curve at that point will be y equals 8x minus 4. Okay. Now, other concept time. If the gradient of the curve is the same as the gradient of the tangent, that's fine, but there's another thing that we're interested in as mathematicians, and that's a line sticking out at 90 degrees. Okay, to the curve at that point. So the red line is the tangent, and the blue line is what's called the normal. And that's really easy to work out, because if you've done any straight line stuff, then you know that if one gradient m1 is perpendicular to another gradient m2, then that means that either m1 times by m2 equals negative 1, or another interpretation of that is that one gradient is the negative reciprocal or the negative flip of the other. So let's suppose I wanted to work out the normal of the curve at that point when x equals 1. Well, if I knew the tangent had a gradient of 8, then the normal will have a gradient of the negative flip of 8, which is the flip of 8 is 1 over 8, reciprocal of 8 is 1 over 8, and make it negative, minus 1 over 8. If the tangent had been minus 1 over 5, then the normal would be negative times negative, which is positive, and the flip of 1/5 is just 5. It's the negative reciprocal. You flip it, and then you change the sign of it. Okay, and now derivatives are really good tools for finding normals and tangents of curves. Okay, now I've got a couple of examples to go through. So, this question, the first part, if you remember, we did a second ago. And if you want to pause it, go for it and refresh yourself that you can do that again. And go through the equation of the tangent. But I'm going to cheat and go back up. Where was it? It was here. And the answer was 1 plus 24x to the minus 2. Okay, 1 plus 24x to the minus 2. So find an equation of the tangent to the point where x equals 2. Well, the first thing I need to do is work out what y is at that point. So if I sub in 2, then y equals 2 plus 3, which is 5, times by 2 minus 8, which is minus 6, all over x, which is 2. So I've actually got minus 30 over 2, which is negative 15. Okay, so there is a function that has a coordinate on it called 2 minus 15, and I want to work out the equation of the tangent. If I want to work out the gradient of that tangent, that straight line, then I plug 2 into this thing over here. What is that going to be? So we write this, we say dy by dx evaluated at x equals 2, 1 plus, now 24x to the minus 2 is the same as 24 over x squared. Well, that's going to be 2 squared, which is 4. So 24 over 4 is 6, 1 plus 6, that gradient is 7. So now I've got y equals 7x plus c. I know the gradient is 7. And now I know that y is minus 15, x is 2. So when y is minus 15, x is 2, so 7 times 2 is 14 plus c. If I minus 14 from both sides, minus 15 minus 14 is minus 29. So the equation of the tangent is y equals 7x minus 29. So the tangent has a gradient of 7 and a y-intercept of minus 29. Okay, let's have a crack at another more complicated question. Okay, the curve has equation blah, and the point P has coordinates 2, 7. All right, I'll tell you what, you pause this first. You pause it, you have a go. Worst case, you're wrong. Spend 10, 20 minutes and I'll go through it. Okay, so back on. Curve C has that equation. The point P is coordinates 2, 7. Show that P lies on C. Well, that's easy. We just have to show that when I sub 2 into this to the x, then y is 7. So 2 cubed is 8, minus 2 lots of 2 squared, or 2 squared is 4, 2 lots of 4 is 8, minus 2 plus 9, what does that equal? The 8s and the 8s cancel. Minus 2 plus 9 is 7. That is indeed equals to 7, so yes, it does. Part B, find the equation of the tangent to C at P. Okay, so I'm going to need to find the gradient function of this, i.e. what is dy by dx. And then 3 comes down, so that's 3x, subtract 1 from the power, so that's 2. The 2 comes down, so minus 2 times 2 is minus 4. Subtract 1 from the power, that's x to the 1. 1 comes down, so that's minus 1. And then 1, the power minus 1 is 0, so x to the 0 is a constant. And the 9 disappears when you differentiate it. Okay, so dy by dx is 3x squared minus 4x minus 1. And I want to work out dy by dx evaluated at when x is 2. So this is going to be 3 lots of 2 squared minus 4 lots of 2 minus 1. So all I've done is substituted it in. 2 squared is 4, 3 lots of 2 squared is 12, minus 4 lots of 2 is 8, minus 1. So it looks like the gradient is just 3. So I've got the gradient is 3, x is 2, and y is 7. So y equals 3x plus c. When x is 2, I've got 3 lots of 2, so that's 6, plus c equals the y is 7, c is clearly 1. So the equation of the tangent is y equals 3x plus 1. This is the tangent. Final answer. Okay, the point Q also lies on C. Given that the tangent to C at Q is perpendicular to the tangent to C at P, show that the coordinate of Q is 1/3 2 plus root x. Okay, so if it's perpendicular, that means the gradient of the tangent on the curve to Q is the negative reciprocal of 3, which is minus 1/3. Okay, so that means our gradient function, dy by dx, which is 3x squared minus 4x minus 1, must equal minus 1/3. So this is the quadratic we need to solve. And now there's various ways of solving quadratics, and I'll be looking at them in more detail. But essentially, if I times everything by 3, so that becomes 9x squared minus 12x minus 3, this equals minus 1. Then I add 1 to both sides. Essentially, I have to solve 9x squared minus 12x minus 2 equals to 0. And yeah, however you want to solve quadratics is absolutely fine. Personally, I am probably going to use the quadratic formula, which is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a, and this solves quadratics in the form of ax squared plus bx plus c equals to 0. So if we compute this really quickly, x equals minus b, so if b is minus 12, minus minus 12 is 12, plus or minus the square root of b squared, or 12 squared is 144, minus 4 lots of a times c. Well, 4 times minus 2 is minus 8. Minus 8 times 9 is minus 72. So that's 144 minus minus 72. So it's going to be plus 72. 4 plus 2, 6. 7 plus 4 is 11. Carry the 1. That's 216. And then 2 lots of a is 18. So x equals 12 plus or minus the square root of 216 over 18. We did surds the other day. I know that 216 is 6 times 36, it's 6 cubed. So this is actually going to be 6 root 6 all over 18. I noticed that 12, 6 and 18 are all multiples of 6. So if I divide top and bottom by 6, I get 2 plus or minus root 6 over 3. And yeah, so I'm going to have one answer being x equals a third, lots of 2 plus root 6. And I have another answer, x equals a half of 2 minus root 6. And now I can immediately discredit the bottom one, x, oops, not a half, it's a third, you silly boy. I can immediately discredit the bottom one because 2 minus root 6 is clearly negative. And we can't have a negative x value. Look, x has to be positive. How do I know that 2 minus root 6 is positive? Well, 2, if you think about it, is root 4. Clearly, root 6 is bigger than root 4. I mean, if I was to order the numbers, root 0 is here, then root 1, then root 2, then root 3, then root 4, then root 5, then root 6, and so on. Clearly, root 4 is smaller than root 6. So if I try to minus a bigger number from a smaller number, it's going to be negative. So that root doesn't exist. So that's going to have to go bye-bye. So yes, the only answer appears to be 1/3 of 2 plus root 6, which is exactly what they wanted. Okay, yeah, moderately tricky. Okay, so this is the final bit. We're in the home stretch now. Okay, so I am massively selling this short. There are so many things you can do with calculus, differentiation, the opposite of differentiation, which I'm just going to spoil it now. It's integration. You can probably tell it from the plan. Right. I am only going to go through a couple of things today. It's already been an hour. I promise I will go through more. There's so many, I'm not going to be able to do it justice. But another thing you need to learn, definitely, the foothills of the mountains that are calculus, is you need to be able to look at graphs, understand behavior, and use calculus to kind of understand what's going on. So, let's talk about graphs. Well, let's suppose I've got that good old friend, where is it? My y equals x squared function. And it shouldn't be too much of a jump now. dy by dx is just 2 lots of x. And I want to just clarify a couple of things. I mean, I can write something like this. F of x. when x is positive, then that means dy by dx is also positive. Do you agree? Because when I'm on the right hand side of the graph, and really I should have labelled my axes, this is x and this is y, then no matter where I am, I'm going to have a positive upward sloping gradient. Now in this particular example, when x is 0, this means dy by dx is also 0. And that should be pretty obvious too. It's just a flat thing there. It's got a 0 gradient. It's where it bounces on the x-axis. And then finally, in this example, when x is less than 0, then dy by dx is negative. It has a downward gradient. Well, let's look at that. From here, it's sloping downwards from left to right. Okay, now here's a couple of key things. One, when a graph is strictly sloping upward like this, we say that's an increasing function. So if somebody asked me, okay, Mr. Pope, where is y equals x squared an increasing function? Well, I'd say, well, that's everywhere where the gradient is positive, which means the first derivative is positive. So where it's an increasing function is where the derivative is positive and the gradient's positive, and that's where x is 0. X is greater than 0. Okay. Next thing is when the gradient's negative, as you can guess, that is a decreasing function. That means as the function goes along, it's going down in value. It's decreasing. It's a decreasing function. Okay. And similarly, if someone asked for y equals x squared, where is it decreasing function? You would say it's when x is less than 0. Because when x is less than 0, the gradient in that region is less than 0, which is negative. Therefore, and the first derivative is negative. That's the same. It's another way of saying the same thing. It's a decreasing function. Now, similarly, when the gradient is 0, we call this a stationary with an A, like standing still, stationary, or a turning point. Could also call it a vertex. And typically stationary points, turning points are what we call it. Yeah, and essentially this is where the gradient is 0. In this case, the y equals x squared graph, the turning point is a minimum. Because if you think about it, on the y-axis it goes up to infinity, but the lowest the y value can be is at 0. It outputs a minimum y value at that x value of 0 because the derivative is 0. It's a turning point at that point. Okay. Now, there's various other things. Okay. Now, let's go over here. What happens if we take other derivatives? Now, if I write something like d2y by dx squared, that just means I've taken the first derivative of dy by dx, i.e. I've differentiated y twice with respect to x. It's exactly the same as f double dashed of x. If I was to write d3 by dy dx cubed, that is d by dx of d2y by dx squared, which is the same as d by dx of d by dx of dy by dx. It means I've taken the third derivative, or I've differentiated 3 times with respect to x. And if you really wanted to, you could call that f triple dashed of x, and so on and so on. These higher derivatives have so many different applications in statistics, in complex geometry, in Taylor series, analytic functions, so many different uses, and being able to calculate higher derivatives is so useful. I can't overstate it. But in the context of graphs, higher order derivatives, you only really need to go up to the second order before you get something useful. So let's suppose that I've got a function where dy by dx is 0, so it's a turning point, and the second derivative is negative. Well, what's going to happen here? Well, think about it. At a certain point, it's got a flat gradient. And then what the second derivative is saying is it's saying the rate of change of the gradient. How does the gradient change as you change x? Well, if it's a negative change, that means it's gone from a positive to 0 to a negative and more negative. So what kind of function would it look like if it's gone from a positive gradient to a negative, to a 0 to a negative gradient? Well, it's going to look like this, isn't it? Positive, less positive, less positive, 0, and then negative, more negative, bush. So in the case when the first derivatives, well, look, it's gone from a really positive gradient here, then a less positive gradient, so the gradient's decreasing, and then the gradient's decreasing more, and then the gradient's flat, and then it's slightly negative, and then it's more negative, and then it's way more negative, and it's running out of control. This we will call a maximum. There is a maximum of this curve. Now, if the first derivative is 0, but this time the second derivative is positive, what do you think is going to happen? Well, that means the gradient has gone from a negative to 0 to a positive. The gradient's constantly increasing. So if here's the flat baseline function, it's gone from a negative gradient to a 0. Oh dear, that's terrible. It's gone from a negative to 0 to back up again. Right? Look, it's gone from a negative gradient here, going downwards, less downwards, 0, and then it starts increasing. At every point of x, the next, going from left to right, the gradient is constantly getting bigger and bigger. It's going from a less negative to a less negative to 0 to positive to a bigger positive and so on. And this is a minimum. Now this is really useful because being able to use the second derivatives like this lets us find local minimum and maximums of curves. And we're going to be talking more about this in graph sketching, but we can actually use this analytically to find out minimums and maximums of functions, and we'll be looking at that soon as well. There's another phenomena, graph sketching you have to be really careful of, and that's when the second derivative is 0. Okay, and at this point, you need to do more work. There isn't really a shortcut, but it could be a point of inflection. Well, in actual fact, it is always an inflection point, but there's various there's various ways that inflection point could be. Now, the reason why I'm hesitating is because, look, if you think about it, for this curve, it's gone positive to 0 to negative. And for this curve, it's gone from negative to 0 to positive. So it's gone from positive to negative or negative to positive. Here, it's not entirely obvious if it's gone from positive to 0 to positive again or negative to 0 to negative again. And you're probably thinking, like, what on earth? What do those functions look like? Well, I mean, there's other things as well. Essentially, you need to do more work. You need to analyse this a bit more. There's no shortcut to this. And it's always a good thought experiment to think about it. And there's hard and fast rules if you Google inflection points. But to be honest, I'd rather not. Well, not that I'd rather not, but I think as long as you're prepared to realise that you kind of, it's not as straightforward as that, and it gets you thinking. I'd rather you not just memorise a bunch of rules. I mean, what does it mean to go from a positive gradient to 0 to positive again? Well, let's take the y equals x cubed function. It goes like this. Oh, that's probably not as good. Let's say it's like that. Okay, so at this point here, the gradient is flat. but beforehand it was a positive gradient, still positive. It flattens off at 0, but then it goes back to being positive again. And this is very typical of a y equals x cubed function. And similarly, a negative to 0 to negative again would be like a negative x cubed function, where at this local point here, that gradient would be 0, but it's gone from a negative gradient to slightly less to 0 to more negative. The gradients are always negative again. Okay, so essentially when the second derivative is 0, you need to do more work. There's various ways of doing that. We'll discuss them later. You could just substitute in points either side of it if you want to do some bucket maths. I don't generally approve of that method because you could be missing off, in theory, different behavioural issues, but you know, if you've got reason to believe you won't do that, then I guess it's fairly valid. So it's probably just best to round off today with a few examples, but essentially you can optimise things by taking the first derivative, setting it equal to 0, because you know that it has to be a maximum or minimum when it's 0, and then using the second derivative to check whether it is a maximum or minimum. And I'll probably just go through some examples to check that thing. So, I mean, if you want to try on your own, pause it now, but I'm going to go through it. Okay, so the curve C with equation y equals x to the 4 minus 8x squared plus 3, find dy dx. Well, that's relatively easy. The 4 comes down, so that's 4x, subtract to power 3. The 2 comes down, so minus 16x to the 1, and the 3 disappears. Find the coordinates of each of the stationary points. Well, that is when dy by dx equals 0, so 4x cubed minus 16x equals to 0, which means if we take a factor of 4x out, this is x squared minus 4 equals to 0, and this is just 4x times by a difference of squares, which is x minus 2 times x plus 2. So either 4x is 0, which means x is 0, or x minus 2 is 0, which means x is 2, or x plus 2 is 0, which means x is minus 2. Now, those are all the x values. It says find the coordinates of each of the stationary points. So because y is a function of x, for each of the x values I need to find an appropriate y value to go with them. Got to read the question, not skip any bits out. So there's 3 turning points, there's 3 stationary points here. And I've got to find the x and y values for each one. So I've got all the x's, now I just have to sub them in. So y is clearly 3 when x is 0, because 0 to the 4 minus 8 0 squared is that. That's easy. Maybe I should tidy this up. So x to the 4 is x squared times by x squared, and minus 8x squared is going to give a minus 8. So when x is 2, oh, this is interesting, because when x is either 2 or minus 2, x squared is still 4. So 4 times 4 minus 4 is 4 times minus 4, which is minus 16, and minus 16 plus 3 is always minus 13. So x is 0, y is 3, x is 2, y is minus 13, and x is minus 2, y is minus 13 are going to be my answers. Okay, easy peasy. Determine the nature of each stationary point. Do you remember? I've got to differentiate them and see whether the second derivative is negative or positive. Okay, so if the first derivative is that, what is the second derivative? Well, 4x cubed becomes 12x squared, and minus 16x becomes minus 16. If I take a factor of 4 out, that's 4 lots of 3x squared minus 4. Okay. So, what happens with the second derivative at the point x equals 0? Well, I will get 4 times 3 lots of 0 squared minus 4, which is minus 16. Now, because the second derivative is negative at that point, that means it's a maximum. It's a maximum. And then d2y by dx squared evaluated at the point when x equals 2. Well, it's going to be the same It's going to be the same for both, isn't it? X is minus 2 and x is 2 because I've got this x squared popping up again. So that's not going to be able to tell the difference between a 2 and a minus 2. So 3 lots of 2 squared is 3 lots of 4, which is 12. 12 minus 4 is 8. So this thing is always 8, whether x is positive 2 or negative 2. And 8 times 4 is 32. And because that's positive, these are both minimums. Interesting. So you're probably thinking, how does that work? Okay, so let's just plot them really quickly. When x is 0, y is 3. So that's the point 3 on the y-axis when x is 0. When x is minus 2, which is there, y is minus 13, which is down there. So I know that's a point, that's a point. And when x is positive 2, y is minus 13. So positive 2, minus 13 there. And I know that when x is 0, it's a maximum. So it's going to look like that. It's going to bulge like that. And the other two values, it's minimums like that. And they're the only two turning points. So I know that these must join up, these must join up. This looks like this, and this looks like this. So if anything, I can tell straight away that this function looks like a kind of curvy W. It looks like a W, but instead of straight bits, it's got like curvy, bendy bits. Okay, part D. The point A on the curve C has an x-coordinate of 1. Find the equation to the normal to C at A. Ooh, okay. So what was dy by dx? It was this thing over here. So when x is 1, I've got 4 lots of 1 cubed. So the gradient is 4 minus 16 lots of 1. So the gradient's minus 12. And if I want the normal, I need to do the perpendicular gradient. So the normal gradient is actually going to be 1 over 12. If the x value is 1, what's the y value? When x is 1, I've got 1 to the 4, which is 1. Minus 8 lots of 1 squared is minus 8 plus 3. So 1 minus 8 plus 3, that's going to be minus 4. So I've got y equals 1/12 of x plus c. When y is minus 4, x is 1, so that's 1/12 plus c. Minus 4 is minus 48/12, so if I minus 12, it's minus 49 over 12 equals c. So then y equals 1/12 of x minus 49/12. If I times everything by 12, because it wants it in the form of ax plus by plus c, where a, b and c are integers, which means I have to get rid of these fractions. Times everything by 12 is 12y equals 1x minus 49. And I want that equal plus a constant, so that's going to be 12y minus x plus 49 equals to 0. That's the form they want it in. So a bit complicated at the end, but that's the general gist of what's going on. Okay, next question. This is going to be an optimization question. Pause the video and have a go yourself. Right, on a journey, the average speed of a car is v meters per second. For v is greater than or equal to 5, the cost per kilometre, c pence, of the journey is modelled by that. Using this model, show by calculus there is a value of v for which c has a stationary value and find this value. Okay, so change a variable here. We're not dealing with y's and x's, but what are we trying to do? We're trying to minimise c, so minimising c with respect to v. That's what we're looking for. So 160 over v is 160v to the minus 1. The minus 1 comes down, so it's minus 160v. Subtract 1 from the power is minus 2. And then v squared, the 2 comes down, but this is 1 over 100 times v squared. So 2 times 100 is plus 1 over 50. V and 2 minus 1 is just that. So we have this. Okay, now if we want to find a stationary value, then we want to set this equal to 0. So what can we do here? If we can times by v squared, then I'll have minus 160 plus 1 over 50 v cubed equals to 0. And if we times both sides by 50, what's going to happen there? 560 to 30, 8,000. So v cubed plus from the minus 8,000 there equals 0, which means v cubed equals 8,000, and the cubed root of 8,000 is just 20, isn't it? Okay. So there is a stationary point for c, i.e. when the gradient or the dc by dv equals 0, and that value when it happens for v is 20. Justify that this value gives a minimum. Okay, in that case we need to find the second derivative and compute that. So the minus 2 comes down, so that's positive 320. V subtract 1, so that's minus 3. And 1 over 50v just becomes 1 over 50. Okay, so clearly this is always positive, because this is going to be 320 over 20 cubed plus 1 over 50. I don't need to calculate what that is. That's a positive number plus a positive number, therefore it's a minimum. I can just tell it's a positive number. Find the minimum value of c and hence find the minimum cost of a 250 km/mile journey. Okay. Oh, I see. Okay, fine. So find the minimum value of c. So the minimum value of c is when v is 20. So I just sub that value back into there. So c equals 160 over 20, which is just going to be 8, plus 20 squared, which is 400 over 100, which is going to be 4. So 8 plus 4, so that's 12. So since c is the cost per kilometre in pence, then I do 250 times by 12 will give me how many pennies? So if I put 4 from there into there, that's the same as 1,000 times by 3, which is 3,000 pennies, divided by 100, that's going to be exactly £30. So it looks like if the average speed of a car is 20 meters per second, that will give a minimum cost per kilometre in pence per kilometre, and for a 250 kilometre car journey, that's going to be £30. Yeah, nice. Okay, last one. Ooh, is this the last one? Yeah, okay. The figure below, give it a pause, try it yourself. If not, hang on. Okay, so the figure below shows a solid brick in the shape of a cuboid measuring 5x by x by h, as shown. The total surface area of the brick is 720. Right. Show the volume of the brick, V, is given by that. Okay, well, let's think about it. V is 5x times x times h, which is 5x squared h. And then we look at this and go, what the hell? Where did the h go? So what that probably means is we have to use this information to get h as the subject and back substitute in. So let's think about it. The total surface area, S, is 720. But that's the same as 2 lots of the front side, because it's a cuboid. So that's 2 lots of 5x times h. So that's 10xh. Plus 2 lots of these side panels, or x times h times 2, that's a 2xh. And then there's going to be 2 lots of these top panels, because the top and bottom, so that's 5x times x. So it's going to be a 10x squared. Right, if we tidy all this up, 10xh plus 2xh is 12xh. That's plus 10x squared, and that equals 720. I can divide by 2 both sides to get 6xh plus 5x squared equals 360. If I want to make h the subject, then I'll do 360 minus 5x squared equals 6xh. And if I divide both sides by 6x, I'll get h equals 360 divided by 6 is 60 over x minus 5x over 6. Okay, now I take this value and I whop it in over here, substitute it. So v equals 5x squared times by h, which is 60 over x minus 5x over 6. So let's distribute that out. 5 times 50 is 300. X squared times 1 over x is just x. Minus 5 times minus 5 is minus 25x. But then I've got an x squared times that, so it's an x squared. And then don't forget the over 6. So were we aiming for 300x minus 25x squared, x cubed, sorry, over 6. Sorry. X squared times an x is x cubed, you silly boy. Yes, cool. In there. Bang. So wasn't really a test of whether you could differentiate stuff. It was more of a problem solving thing. And unfortunately, this kind of problem solving you're just going to have to get used to with more difficult maths. To be honest, this is pretty straightforward. Find the value of x for which v is stationary. Okay, so we want to find dv by dx and set it equal to 0. So 300x differentiates to 300, that's easy. And 25x cubed, well the 3 comes down, and 3 over 6, that will become a 2, so this becomes minus 25 over 2. X, instead of cubed, it's now squared. Okay, now, if 0 equals 300 minus 25 over 2x squared, then that means 25 over 2x squared equals 300. If I times by 2, this is 600 equals 25x squared. How many 25s are in 600? Well, there's 4 25s and 100. And there's 600s and 600. So 4 times 6 is 24x squared. So x equals the plus or minus square root of 24. But we're going to take the positive square root of 24 because x is clearly a dimension here, and you can't say your brick is minus root 24 wide. And root 24, well, what's the largest square number that goes in 24? That's 4, so that looks like this is 2 root 6. So, hold on. Find the value of x for which v is stationary. Yes, x is 2 root 6. C, calculate the maximum value of v, fully justifying the fact it is indeed a maximum. Okay, so let's check. The second derivative, let's check it is a maximum first. Well, 300 disappears. 2 times minus 25 over 2 is just minus 25, and this becomes minus x. Well, clearly, 25 times 2 root 6, and the negative in front is going to be less than 0 for all positive x. So this is indeed a maximum. The second derivative is negative, it's a maximum. And if it's positive, it's a minimum. Now I have to find that value of v. So now I just plug 300 lots of 2 root 6 minus 25 over 6 times by 2 root 6 squared. So v equals, does it want it? Yeah, no. 300 times 2 root 6 is 600 root 6. 2 root 6 squared is 4 times 6, which is 24. The 24 and 6 will cancel, so I'll give a 4. 4 times 25 is 100. So it's that, 600 root 6 minus 100. Or if you want to, it's 100 lots of 6 root 6 minus 1. And this was in centimetres cubed. So this should have been centimetres cubed. This should have been in centimetres. And we're done. So yeah, this was an optimization problem because we're trying to optimize v for a given value of x. X could have changed. So that brick could have been manipulated in loads of different ways. Anyway, guys, I hope this wasn't too much of a, a brain jar. But yeah, have fun. And I'll be around in Google Classroom to answer any questions.